Hello guys, today I'm gonna start modern physics and the first topic is about blackbody radiation. A perfect blackbody is one which absorbs totally all the radiations of all wavelengths incidents on it. We have studied that when energy radiation falls on a body, then there are three actions that some of the radiations may be reflected, some radiations may be absorbed by the body, and some may be transmitted through the body. But a black body neither reflects nor transmits any of the incident radiation. On the other hand, when such a body is heated, it emits radiations of all possible wavelengths. These radiations are called blackbody radiations. It means that at lower temperature, blackbody absorbs 100% of energy radiations incident on it, and at higher temperature, it emits all the wavelengths. Example: sun, stars are the blackbody which emits all possible radiations. But is there any blackbody that absorbs 100% of the incident radiation on it? Yes, but not 100%, approximately 99%, such as carbon black, platinum black, and also lamp black are good approximation of blackbody. They absorb about 99% of the incident radiation. One more thing, that we can see any object when it reflects lights towards our eyes, as a black body does not reflect and transmit light, so it is invisible, means black. So black is not a color, rather in the absence of light we see objects black. Now I will explain about black body in practice. The simple and most commonly used black body was described by Ferry. A closed chamber, say a hollow sphere, a closed chamber having a narrow opening at one point O. At one point O is a perfect absorber and is used in practice as black body. The radiations which enter the sphere through the narrow opening O suffers multiple reflection and is finally absorbed. Similarly, if the enclosure is heated to a uniform high temperature, then the radiations coming out of the opening O are called blackbody radiations, and the hole in Ferris blackbody act as a perfectly blackbody. Let's talk about distribution of energy in the spectrum of a blackbody. The intensity of radiation emitted by blackbody is not uniformly distributed over the whole range of wavelengths in the continuous spectrum emitted by it. It can be easily observed when a blackened platinum wire is electrically heated or a iron rod is heated, it becomes dull red at about 500 degree Celsius, cherry red at about 900 degrees Celsius, orange red here, orange red at 1100 degrees Celsius, and yellow at 1250 degrees Celsius, and finally white, and finally it become white. This shows that as the temperature rises, the radiations emitted more and more of shorter wavelengths. In other words, as the temperature is raised, the maximum intensity of radiation shifts towards the shorter wavelength side. We observe that temperature increases and dull red changes to cherry red and wavelength become short. Similarly, in the increase of temperature, cherry red changes to orange red and orange red to yellow, yellow to white, and so we see wavelength also decreases. And from this practical observation, a graph is plotted between intensity of radiation or energy density and the wavelength. From the graph, we can clearly see that the value of wavelength lambda for maximum energy decreases with increase of temperature. So, as the figure, the wavelength corresponding to maximum energy represented by the peak of the curve shifts to shorter wavelength side as the temperature increases. That is, lambda m into t is equal to constant. And this is the equation of Wien's displacement law. So this confirms Wien's displacement law. The total energy of radiation at a particular temperature is given by the area under the curve corresponding to the temperature. Suppose this graph corresponding to the temperature and the horizontal axis. If we talk about this graph, then corresponding to this temperature and the horizontal axis, and this is the area, and the area is found to be proportional to fourth power of the corresponding absolute temperature, that is E is equal to sigma into T to the power 4, and sigma is called Stephen's constant. This is nothing but Stephen's law, hence this verifies Stephen's law. Wien's relation for distribution of energy with wavelengths agrees with the experimental curves for short wavelengths, but for long wavelengths there is a deviation. Lord Rayleigh and later James therefore tried to determine the form of the relation for distribution of energy with wavelength within the range lambda and lambda plus d lambda, and the expression comes out to be E lambda d lambda is equal to 8 pi kt by lambda to the 4 into d lambda, and E suffix lambda proportional to 1 by lambda to the 4. This law agrees with experimental result for long wavelengths only. This is the experimental curve, this is Rayleigh-Jeans curve, and this is Wien's curve. So for short wavelength, Wien's curve agrees with the experimental curve, but Rayleigh-Jeans curve does not agree for short wavelength. But for long wavelength, Rayleigh-Jeans curve agrees as E lambda then decreases, and for long wavelength, Wien's curve does not agree. And if we take, you can take these notes, blackbody in practice, distribution of energy in the spectrum of a blackbody, discussion, Stephen's law, Wien's displacement law, and Rayleigh-Jeans law. See here, for the high value of lambda, E lambda decreases, so its E lambda decreases. So for the high value, E lambda decreases, and it's agree with the experimental curve. Thank you.